Alright, hi Nixon. This is the chapter 6 practice test. I've had a read through. Everything except for this one makes sense. So, yeah, I'll just skip question 3. Sorry about that. I actually have no clue how that one works. So starting with question 1, we've got two graphs and it's asking which one represents a polynomial function. So, polynomial function has two main conditions. First one is continuous smooth curves. So for example, if you had an absolute value graph, it would look like that, right? And that's obviously not smooth, so that can't be a polynomial function. If you have a piecewise function, it could look something like that. Obviously there's a break there, so it's not a continuous smooth graph, so that can't be a polynomial function. So in general, anything with a break can guaranteed not be a polynomial function. And here, over up there, I'll draw it because the quality is not great. It sort of looks like this. And this is a clear break, right? Otherwise, it would just continue the line through the thing. So, because there's a break there, it's indicating that there's an asymptote at x equals 0. It's like along this line here, the function is undefined, and therefore it's not continuous and smooth, and therefore it can't be a polynomial function. The second doesn't even need to come into play for this one, for testing the first one, because it's already failed the first condition. But for the second graph, to confirm that it's a polynomial graph, or polynomial function rather, is that it has to continue infinitely in both directions. So, as we can see, with this second one, it continues upwards, and it continues downwards, and obviously it's at a weird rate, but it keeps continuing to the left, and it keeps continuing to the right. So it'll be true for all of values of x, and it'll be true for all values of y, and therefore it is a polynomial function. And so the answer to this one is number 2 only, B. Second one, which graph represents the polynomial function f of x equals negative 3x squared plus 2x minus 5? So all of these do extend both directions infinitely and are smooth continuous lines. So they are all actually polynomial functions. But instead of asking the same thing as before, this is saying which one is this specific polynomial function. And one trait that's really easy to look at is just the y-intercept. So say if you let x equal 0, if this is 0 and this is 0, anything times 0 is 0. So this whole thing becomes 0 and this whole thing becomes 0. And so all we get left with is f of 0 equals negative 5. So it's saying along this middle line, when x equals 0, the function will equal negative 5, right? So let's look at which ones equal negative 5. This first one does intercept at negative 5, so we'll just put a tick there, that's true. This one intercepts at 0. I should probably pick a different color to make it a bit more obvious. Negative 5, 0, so that can't be true, we'll cross it out. This one intercepts at just above 4, so it can't be true, we'll cross it out. And this one intercepts at 5, so that also can't be true, we'll cross it out. So it has to be A. Perfect. Like I said, we're skipping 3, just because it makes no sense, to me at least. Question 4, a spherical weather balloon is being inflated. The table shows the volume of the balloon at different times. Use cubic regression to determine the volume of the balloon after 5 seconds. Okay, so we've got our numbers in our table here, and I'm going to leave this to go to Desmos, so I'm assuming you have the numbers in front of you. Okay, we're over at Desmos now, and I'm just going to get my values in front of me. Hopefully you've got the question 4 table in front of you, and just teaching you how to enter a cubic regression model in case you haven't been taught before. you're going to click this plus sign on the top left and enter a table. As you can see, we've got x and y values. Your x value is always going to be the one that's changing consistently. So in this case, that's time. If time is in it, it'll always be time. And then your y value is your other one, obviously. So our volume in this case. And you're just matching it up. You're basically just remaking the table that you had given to you. 1070. Perfect. And then once you finish that, you may be like weirdly arranged. There's this little magnifying glass here. And if you just press that, it brings you to all of your data points and to the correct scale. So that's really useful. And then after you've entered those, we're going to put in y1, because if you look at the top of the table, that's what our y variable has labeled on it, the subscript of 1. And then we go and get a tilde, which is this little squiggly line, instead of an equal sign. And that is the sign basically saying we're doing a regression. And we're just going to grab a x cubed plus, and we're just entering a general form of a, x1, same way as we did y1, b x1 squared, a general form of a cubic function, plus c x1 plus d. And you'll notice we've got a cubic function that goes through all of our points. And that's our regression line. And now the question says, use the cubic regression to determine the volume of the balloon after 5 seconds. So if you hold down on the line with your mouse or finger, whichever you're using, I'm using my iPad, and you find where the left side number, the x value, is 5. In our case, it says 2515. And I know there's no answer that says 2515, but I double checked it and the answer is definitely just wrong. There's something on the internet that corrects it as well. That is the actual answer, but obviously we're just going to go for the closest one, which is C, so 2475. So we'll go back to this and choose C, 2475. Okay, question 5. Consider the graph below. Or the graph shown rather. Now this confused me for ages when I was reading it, because this graph is so low quality it's not even funny. But there is a horizontal line that just goes through, like there, right? Through 3. So, I don't know exactly what it's asking for. So I'm just gonna fill in horizontal, straight line. I don't know if that's really what it wants, but yeah, it's a bit, you could put in so many different words there, it doesn't really make sense as a question. The next question is a lot more obvious. How many x-intercepts are there? Well, x-intercepts is when it crosses the x-axis, which is this line down here, and obviously it won't ever cross that because it's parallel with it. So 0 x-intercepts. And how many y-intercepts? Well, it's when it crosses this vertical line, the y-axis. And there's only one of those, and that's at y equals 3. So, and one y-intercept. The graph extends from quadrant what to quadrant what. For any Cartesian plane, the quadrants are 1, 2, 3, and 4. Don't know why I did Roman numerals. That's just the way it was taught to me. You can literally just do 1, 2, 3, 4. So it sort of counts like anti-clockwise, starting from the top right. So because it goes in both directions, you could say it goes from 2 to 1 or 1 to 2. But I've never actually been told to use this as an answer. I just know what the quadrants are. I'm going to say from 2 to 1 because I read left to right, as with any English person. So left to right is from 2 to 1, but it could very well be 1 to 2. I don't know, I haven't looked at the answers for this question. The domain is, okay, I'm actually going to look at the answers for this. Bear with me, because I don't know what notation it wants them in. Question 5. Okay, perfect. So, there's many different functions for domains, but not functions, notations for domains. That's why I double checked. But for this one, they're just saying that because it goes across, like it extends infinitely, right? So it doesn't matter how long you make the x-axis and what numbers, this could be like negative infinity, positive infinity. It will reach it, and therefore, if it's any real number, it will encompass that x value. So this is the sign for an element. It sort of looks like an E, so that's the way I remember it. And then instead of just writing R, you do like a fancy R. This is the notation that signifies real numbers. On their answer, actually, they just have a normal R. But, yeah, that's not the way you're supposed to do it. So, X is an element of all real. And the range is going to be Y is an element of... Oh, wait, no, it's just a straight line. Okay, perfect. So it's just Y equals 3. Because it doesn't matter, again, it doesn't matter how far you go sideways. This is always going to be like the line that it travels along. Y is never going to be anything except for 3. You can plug in any x value. You could be at like negative 100. You go up and it's at Y equals 3, right? So the range is just from 3 to 3. Therefore, the range is just Y equals 3. And there is how many turning points? A turning point is defined as when the function changes direction from up to down or down to up. It's actually when the concavity changes, but I don't think you've been taught that. I don't think you would have needed to be taught that, so I won't go into that. But it's a straight line. It obviously doesn't turn. Like, that's more of a common sense question. You don't need maths knowledge to know that. 0 turning points. And this graph represents again, you could put tons of words into this. I'll just go off what their answer says, because you could say a bunch of stuff. But linear function makes sense completely, because a linear function means consistent gradient. If you look at a polynomial like the one we had up here, or any of these ones, I'll just draw that shape down here. If you have this, and you draw a line tangent there or there, you see how those are two very different gradients? Like the gradient changes the whole way. Whereas if you have a straight line, a linear line, the gradient anywhere along here is the same. So it's linear. And then consistent, I guess it's just trying to say that... Oh, constant. Oh my word, I can't read. Okay, yeah, it's a constant because it doesn't matter what value of x you put in, the y value stays the same. That would help if I could use my eyes. Y, the way of like saying it is y is independent of x. So if you graphed like how many times will the sun rise per day as your y-axis, and then how many, I don't know, Canadian analogies, how many hockey trophies will Wayne Gretzky win in his lifetime? Like, it doesn't matter how many hockey trophies Wayne Gretzky wins, the amount of times the sun rises in a day is always going to stay at 1, right? So it's going to be constantly at 1. So if you ever have a straight horizontal line, like this one, it means that the y is independent of x, and that means that it is a constant, which makes perfect sense. So I take back what I said earlier about this being weird. This actually makes sense, and hopefully that makes sense to you as well. Constant linear function. Okay, enter the characteristics for each polynomial function. So we've got a lot of terminology here. I'm going to go over them. You can skip forwards if you know them. The degree is the easiest one. It's just the highest power of x. So if you have like x cubed plus x to the 5 plus x squared, a common mistake that people make is they'll like, oh, x cubed is the one that comes first, so the degree is 3. But x to the 5, that's a higher power, so it's 5 as the degree. It's literally just the highest power. So in this one, we've got x, that's like an imaginary 1, and this is times x to the 0, because x to the 0 is 1, right? So the highest degree, the highest power is going to be 1, so the degree is 1. The leading coefficient, hand in hand with degree, it's the coefficient of the degree. So if we have like, again, x3 plus 4x to the 5 plus 3x squared, our degree is 5, and that term, the coefficient is 4, right, because it's attached to that x. So our leading coefficient would be 4 for this one, and for the one they gave us, it's attached to the x, so it's 14. Our constant term, we actually just went over that up here, right? A constant is where it's independent of x, so it doesn't matter what x is, 3 won't change, because it's not multiplying by x in any form. So our constant term is 3. Number of x-intercepts, I'm just going to erase this to avoid confusion now. If we graph this, it wouldn't have any turning points, but it would intercept x, right? Intercepts y at 3. So it looks something like that, right? Number of x-intercepts, it just has 1 here. A good way of figuring out as well is generally the number of x-intercepts will be equal to the degree. That's the maximum number of x-intercepts that it can have. It's not always going to be equal to that, but that's overcomplicating a bit. But for this one, the degree is 1, so we know that it has to be 1 at max, and for any linear function like this one where it's just the degree of 1, the solution will always be 1 for number of x-intercepts. Then y-intercept, similarly, again, if you graph it, it goes through it once. And actually, for any polynomial function, oh wait, it's not number of y-intercepts. Okay, well, it's good knowledge anyways. For any polynomial function, there will only be one y-intercept. If it has more than one y-intercept, like a circle, for example, it indicates that it's not actually a function because it has multiple y values for a single x value. But for this, the y-intercept is just when x equals 0. We went over that up here for this question. So if we let x equal 0, 14 times 0 plus 3 equals 3. So y-intercept is 3. And again, the reason we let it equal 0 is because along this line, x equals 0, right? Because that's like x is -1, x is 1, 2, -2. This one, x is 0. So find where x equals 0, and then find where it cuts through, which in this case would be at 3. Extends from, okay, quadrant, I guess it's saying 3 to 1, so that's 1, 2, 3, 4. It actually passes through quadrant 2, but yeah, the bottom of it is going to be at quadrant 3, and it goes up to quadrant 1 because it has a positive gradient, and it intercepts at 3. If it intercepted at a negative number, it would actually be the same answer, but it would come under like that because the intercept's negative. And if the gradient was negative, 1, 3, gradient was negative, it would start from the top left and go to the bottom right. So it'd go from 2 to 4 instead of from 3 to 1. But in this case, it's from 3 to 1. Domain x is an element of all real. We just covered that. It's like for the graph, it doesn't matter how far you stretch it this way or how far you stretch it that way. It'll still line up with an x value, right? I'll do these lines in different colors. And if it's true for all x, then the domain is x is all real numbers. And the range, same thing. I should really stop erasing the whole thing. The range, this can keep going up and it'll always line up with a y value, and this can keep going down, it'll always line up with a y value, so it is true for all real numbers. So y is an element of all real. Number of turning points, well, it's a straight line, we've been over that, so 0. There's no point where this goes from that to that, or that to that. Okay, how long has this been going for? I don't even know. Hopefully not too long. Alright, next part. The function of j. Okay, this can complicate things a bit for some of them. I don't know what your syllabus entails, so I don't know how deep to go into it. But we'll go with what we know. So the degree is the highest power. So we have 3, 2, 1, and 0. And so x to the power of 3 is going to be our highest exponent, so our degree is 3. The leading coefficient is the one attached to our highest exponent, so it's 9. Our constant term is the one that has nothing, no x attached to it. Now be careful here, because that negative sign in front of the 1 is included in it. That is the whole constant term, because the general form, as we went over earlier, is x cubed plus bx squared plus cx plus d, right? So in this case it's plus -1, even though it just says -1, but d is actually -1. Yeah, so our constant term, -1. Number of x-intercepts. This is where it gets weird. I'm gonna assume that it's a normal cubic, that you don't have to work this out. Like, you can, it's doable. Oh wait, you're allowed to use Desmos. Just graph it on Desmos. Okay. 9x cubed minus 3x squared plus 2x minus 1. I've already forgotten it. 9x cubed . 9x cubed minus 3x squared plus 2x minus 1. X squared plus 2x minus 1. And zoom out. Oh, perfect. It has one x-intercept, and that is somewhere over there. But as you can see, it has 2 turning points, but they're both... Oh, wait. There's 2 x-intercepts? Yeah, 1 x-intercept. Sorry, I don't know why I fluffed around there. Just let it equal 0. And that's the point where it equals 0. Just to show if it wasn't that, you can do like x squared minus 1 equals 0. See how it has 2 points? Because if you just graph x squared minus 1, oh my goodness, this scale is really messing me up here. It cuts through at 2 different points, and those are the red lines. I'm overcomplicating things now, but anyways, our answer is 1. Just graph on Desmos, let the function equal 0, and that'll show you the amount of x-intercepts. I keep forgetting that you're allowed to use it. The amount of y-intercepts, we could cheat. Just go back here. How many times does it cross that middle line? Crosses it once at this point, right? So at -1. And oh, it's not the number of... I keep making this mistake. Okay, y-intercept is just let everything equal 0. It's always going to be the same as the constant, actually. I should have mentioned that earlier. -1. Extends from quadrant to quadrant. As we can see in this one, it extends from quadrant 3 to quadrant 1. But actually, for any polynomial, if the degree is even, and it's positive, it's gonna start from the top left, finish in top right. If it's even and it's negative, it's going to start from bottom left and end in bottom right. If it's odd and positive, it's going to start in bottom left and in top right. And if it's odd and negative, it's going to start in top left and end in bottom right. Which seems like memorization, but it kind of makes sense the more you do graphs and practice and stuff. You'll just notice that. But yeah, we've graphed on Desmos anyways, so we just know. I hope you can use Desmos the whole time and I'm not stuffing you over. If you need, just let me know. I can tell you how to do this without Desmos, like all of this, but it just takes a bit longer. Domain, we know that it stretches the whole way through, and again, you can line up anywhere, so it's all real. And the range, same thing. I won't fluff around too much, we're running out of time. Number of turning points, we did say it's when it changes concavity, so you can see it goes from going like up and in to going that way. So it turns here and here. It's more of a visual thing. It's hard to really like explain without talking about calculus. For me at least, I find it hard. But just think about like if it's pointing in, pushing in on that side and then pushing in on that side. If you can count 2 of those times, then it happens twice. If it just goes like this, then that's just once. If you have like that, that's twice again. If you have like, that's 3 times. Like you kind of get the gist, I think. But yeah, so that one's just, this will be 2. Just double checking that. Yep, that all looks right. Oh, they did theirs in Roman numerals as well. Maybe I should do that. Go back to how I was taught, I guess. And also, I just realized I have like a function thing tonight, so I won't actually be able to do all the videos today, but I'll get them done. Oh wait, you have your exam on Friday. Yeah, I'll get them done like at some point. Hopefully I can call you. I prefer that, so I can know what you actually need help with. Each year the Mapleton Health Department tests about 15,000 water samples, blah blah blah. Use linear regression to complete the statement. Okay, linear regression, just do the exact same thing as before. I'll pull up these numbers on my laptop and go here, plus table x values. We've got the number of samples, 2,500, 5,000, 12,500, 14,000, 16,000, 20,000. And our cost, we've got 200, we've got 2,000, 5,000. Oh, that's 50,000, my bad. 5, 6, 1, that's random. 6, 400, and 8,000. Perfect. And then here, y1, get our little squiggly line, our tilde. And then instead of doing the whole function like we did before, we want the general form of a linear function, which is ax plus b. And a magnifying glass, and wow, just like that, it goes through all the points. Very lovely. And next year, wait. When do I know what next year is? Oh. Oh, okay, so I just need to figure out, okay, what it is at 15,000, sorry. So they're saying, I'll go back to this just so I can highlight what I was reading. I didn't read the question at first, classic mistake. But it's saying the government tests 15,000 water samples, but here it jumps from like 14 to 16,000. So there's no 15,000 point, so you can't see how much it costs for 15,000. So it's easy as pie, you just have to come here, find 15,000, which again, just hold down, go through. 15,000 is 6009537. 6009537. I don't know how accurate they want us to be. Let's double check the answers. 60010. Wait. 6010. There we go. And that's the answer they want. So just rounding. Perfect. And that's the whole thing you sent me. I don't know if this last page is glitched because the answers show question 8, 9, 10, 11. But if there's more questions, I'll just do those. Yep, there you go.